When we pay close attention to chemical reactions, we discover that there is a temperature change associated with most of them. Mix citric acid solution with regular baking soda, sodium hydrogen carbonate, and the temperature of the surrounding water decreases. Drop magnesium strips into room temperature hydrochloric acid, and a thermometer shows the temperature going up. Sometimes you can even feel the heat coming out. That's not all. The more magnesium you use, the bigger is the temperature change. So chemical reactions, we say, can either give off heat energy or take in heat energy. It's like heat is one of the reactants or one of the products. We call reactants that give off heat energy exothermic reactions. Energy coming out of the reaction heats up the surrounding water or air or glass. Reactions that take in energy are called endothermic reactions. Energy is needed by the reaction, so the reaction takes heat from the surrounding water or air or glass. Now, what is happening with the reactants themselves? We remember that the law of conservation of energy tells us that energy is not created or destroyed in reactions. That must mean that in an exothermic reaction, the heat that comes out must be coming from the reacting chemicals themselves. And in an endothermic reaction, the heat that is used to keep the reaction going must be getting stored in the products being formed. Let's talk about exothermic reactions first. When methane burns in air, heat is given off. Many times this is the way we heat our homes. The chemical reaction tells us that 1 mole of methane reacts with 2 moles of oxygen to form 1 mole carbon dioxide and 2 moles of water vapor. But heat is also given off. We can treat heat as a product. This heat warms up the surrounding air, making those air molecules move faster. What is happening to the energy stored in the methane and oxygen molecules? This is potential energy. We have to burn the gases to get the energy out. As the methane burns, the stored energy comes out. The energy stored in the methane and oxygen is greater than the energy stored in the carbon dioxide and water. We symbolize this with a graph called a reaction energy profile. The progress of the reaction is shown on the horizontal axis. Reactants are placed on the left, products are placed on the right. The relative energy of the reactants and products is shown on the vertical axis. In an exothermic reaction, energy comes out. That means reactant energy is greater than product energy. In this reaction, methane and oxygen together have a relatively high energy stored in them when they are formed. 1 mole of carbon dioxide and 2 moles of gaseous water together have a relatively low energy stored in them when they are formed. The difference is 802 kilojoules per mole of methane. The products are 802 kilojoules lower in energy than the reactants. That comes out as heat into the surroundings. The change in energy is downward. We can show the change in internal energy, called enthalpy, symbolized delta H. We can show this delta H, or enthalpy change, as a product of the reaction. But most of the time it is shown on the side of the reaction, as delta H equals negative 802 kilojoules per mole. Exothermic reactions are shown with the reactant enthalpy at the top left of the reaction profile and the product enthalpy at the bottom right. The difference is the heat energy lost as high energy reactants become low energy products. By contrast, in an endothermic reaction, reactant enthalpy is lower than product enthalpy. We have to pump energy into the reactants to force them to become products. A good example is the electrolysis of water. If we pass an electric current through a dilute acid solution, the water breaks up into hydrogen and oxygen gases. Low energy water becomes high energy hydrogen and oxygen gases. The hydrogen can then be burned for fuel to run a vehicle. Endothermic reactions like electrolysis can be symbolized in diagrams that put the reactant enthalpy at the lower left and the product enthalpy at the upper right. Therefore, exothermic and endothermic reactions either give off heat or take it in, and can be symbolized by diagrams like this.